Welcome to the last lecture of this week. So, one of the striking things is that it is possible for a group of waves to either travel faster than their individual components or slower than their individual components. So, typically what happens is that the group velocity is smaller than the velocity of the individual components. So, let us say that I have a group of wave constructed from, let us say, several frequency components put together, and maybe the profile or the shape of the wave is how I have drawn it here, that is right in front of you. So, it shows y as a function of x at a fixed time t. So, what we know is that if there is no dispersion, of course, it is going to maintain the profile and go ahead, but can we define a time frame or a time scale over which this profile will be maintained even in a dispersive medium? Let us start by writing down a series of waves whose frequencies are slightly different from one another. So, it is a group of waves, and here I have suppressed the space part because we are not really going to be interested in that immediately. Capital N is the number of waves that are superposed, and delta omega is of course the small change in frequency, a small change from omega 0. So, if you expand this, you will exactly get this expression, and you should keep in mind that small n is just a running variable. Fortunately, it can be summed. I am going to give the result now and proceed, and I will prove that as a problem a little later. So, as I said, I am going to do this summation separately as a problem, but if you do it, this is the result that you will get. Since we want to get to the central physics of the problem, it is better to stick to simplistic assumptions that would not hide the physics of the problem. So, here that is the reason we stick to all the individual components having same value of amplitude A. Now, let us define an average frequency. Let us call it omega bar, and this should be simply sum of all the frequencies divided by n. So, you have omega 0, then there is omega 0 plus delta omega and so on until omega 0 plus n minus 1 into delta omega, and there are n of these. So, you divide by n. So, let us do that. So, this can be easily simplified. So, I am going to have n times omega 0. So, you will notice that there is one omega 0 in each of the terms that are here, and there are n terms. So, there is going to be n times omega 0 plus there is, of course, if you take delta omega outside, you will have 1 plus 2 all the way up to n minus 1, that will be omega bar. And this summation is easy to do. 1 plus 2 plus 3 up to n minus 1 is a very simple summation to do. So, omega bar will be 1 by n into n times omega 0 plus delta omega multiplied to that summation. It is going to be n minus 1 into n divided by 2. So, this is the expression for average frequency. Now, we will use this in our expression for y that we just got here. So, you will notice that this omega 0 plus n minus 1 by 2 into delta omega is precisely this quantity, which means that leads to a great simplification in terms of notation and also for understanding. Let us call this quantity, which is delta omega multiplied by n, as the bandwidth. So, I will give a different notation. So, it is capital delta omega, which is this. So, all the frequency components that we are using to construct our waveform will fall within this bandwidth. Now, I will write this equation using this capital delta W. So, now I have written the same expression in terms of capital delta W, and in the denominator you will see that I have multiplied and divided by capital N. So, now I can complete this exercise. So, A cos omega bar t into sin delta omega into t by 2, and here. So, this n into small delta omega will be capital delta omega into t divided by 2n. Now, we will take the limit that n is very large, that is. So, if n is very large, this quantity which is the argument of the sine function will become very small. So, in that limit you could always take sin theta to be theta itself. So, that is our next step. Okay, I have done another small manipulation. We have taken the capital N in the denominator to the numerator. Now, let me identify this quantity delta omega into t divided by 2 as theta. So, which means that I am going to have sin theta divided by theta, and you can sort of see where we are headed, but here we have capital delta w. So, it is actually the half the phase difference between the first and the last waveform. So, the time dependence comes from this cos omega bar into t term, and this is the amplitude now. Amplitude itself is time dependent, okay, because theta is simply delta omega into t. So, there is t which is hidden in theta, and amplitude is time dependent, and we have seen this kind of scenarios before. When you add two waves, you see that the amplitude itself becomes time dependent. So, it is not quite surprising that it has happened here as well. And let me also simplify it even further by writing it as capital A times sin theta by theta multiplied to cos omega bar t, and obviously this capital A is equal to A times n. Now, let us analyze what happens to this result at t equal to 0. So, as t tends to 0, sin theta by theta will get to 1, theta is time dependent, it gets to 1, and hence the maximum amplitude would be A itself. This is the limit that t tends to 0 or t is equal to 0. We can draw the profile for y. Let us do that first before we go ahead further. So, I have two parts to this y. One is cos omega bar t, which is simply a cosine function. So, would oscillate at frequency omega bar. On the other hand, I have this amplitude which itself is time dependent, and this average frequency is of course the slower component, and this is going to oscillate much faster. So, now if I put all these information together, this is what I will get. So, this black curve that you see here would correspond to the cos omega bar into t, and that is the slower component, and the faster component is the one shown in red, which would correspond to sin theta by theta part. Of course, you can multiply A if you like. While the cos function does not decay, sin theta by theta does decay, which is why you see the amplitude at time t equal to 0, which is this point at the center, is maximum, but after that the amplitude keeps decreasing. So, at t equal to 0, the amplitude is A, this point. So, you will notice that after some amount of time, the amplitude becomes 0 at this point, let us say here. Now, let us calculate this time interval after which the amplitude goes to 0. So, let us say that after a time interval of t equal to let us say some delta t, the amplitude goes to 0, and this will happen provided that sin theta is equal to 0, which means that basically a statement saying that sin pi is 0. Sin 0 is 0, but we want the next point where sin function goes to 0, that is when theta is pi. So, that is exactly what I have written here. So, this can be rewritten slightly differently. So, delta omega is 2 pi times delta nu. So, if I substitute that here, it will be 2 pi into delta nu divided by 2 into delta t is equal to pi, and of course, pi and 2 will cancel, giving me this expression that delta nu multiplied by delta t is equal to 1. So, this is the all important bandwidth theorem. So, how do we physically interpret this relation? In the following way. Suppose I constructed a profile, let us say some arbitrary profile like this, a wave profile, by putting together a large number of plane waves of frequencies which have a bandwidth delta nu. The question is, how long will it maintain its profile? It is probably going to disperse, but it will maintain its profile for a time interval of delta t. Delta nu, bandwidth, and the time interval delta t are inversely related. So, if you are putting together a large number of waves with bandwidth being very large, then the time interval over which you can maintain its profile is small. If my waveform is just made up of one frequency, there is no group involved here. In that case, it is going to live long enough, in principle for infinite times. I said it is all important because its validity is not just about waves and oscillations. It is valid throughout physics. You can regard it as a fundamental law. In many areas of physics, it appears in different form. For instance, in quantum physics, Heisenberg's uncertainty principle is one manifestation of this bandwidth theorem. Now that we are done with the bandwidth theorem, let us do a few simple problems related to some of the things that we learnt in this week. So, the first of this is the summation which I said I will do as part of the problem. When we were looking at the bandwidth theorem, we were trying to sum cos of omega 0 plus n delta omega into t, but here I have just taken it as e power I omega 0 plus n delta omega into t. So, finally, at some point we will take the real and imaginary parts, and from there we can extract the result that we want. Geometric series, and the common difference is e power I into delta omega into t. So, what I have here is the standard geometric series, and of course, this is a result which can be obtained from a very simple consideration. So, I am not going to derive that result. We are going to use this result sum to n terms of a geometric series. Written the result of summation using the formula for n terms of a geometric series. So, now what we shall do is to do simple manipulations on this. So, first of that would be I will multiply and divide by e power I n delta omega t by 2, and similarly in the denominator I am going to do a similar manipulation. So, I will multiply and divide by e power I delta omega into t by 2 divided by e power I delta omega into t by 2. So, now you can see what will happen. So, if I take this denominator inside this brackets, I will get the following e power I omega 0 into t. So, it is going to give me e power minus I n delta omega into t by 2 minus e power I into n delta omega t by 2. The whole thing is divided by e power I delta omega t by 2 minus e power I, of course, there is going to be a minus sign here, I delta omega t by 2. And of course, the numerators here are still there. So, they will generate for me e power I into n minus 1 into delta omega into t divided by 2. So, this is the expression that I have. Now, it is clear what to do, especially from the structure of the summation that we have, multiply and divide by 2I, these two terms within the brackets in the numerator and the denominator would become a sine function. So, if I factor in that, I can simplify this expression. So, I have the final result in front of me. So, this is the full result of the summation, and if we need the real part alone, you will notice that the only thing that would get affected is this first term here. I just need to take the real part of it, which would be cos of omega 0 plus n minus 1 by 2 into delta omega multiplied to t. And if you remember, when we were deriving the bandwidth theorem, this is exactly what we called as the average frequency. A wave group is made up of two wavelengths. So, clearly there are only two, not n. The wavelengths are lambda and lambda plus delta lambda. The question is, find the number of wavelengths between two successive zeros of the modulating envelope, and here one of the assumptions is that delta lambda by lambda is small, which means that it is much less than 1. So, within the ambit of this assumption, we need to find out how many wavelengths are contained between the modulating envelope. Let us start by writing down the resultant equation. So, now I have a resultant or the sum of two waves. The first one has wavelength lambda, second one has wavelength lambda plus d lambda. The result really does not depend on whether I choose a cosine function here or a sine function here or even a combination of sine and cosine function. So, all that would lead to some phase differences and so on, but the final result will not depend on what choice I make for the solutions of the individual components. So, I have two components here, one is this, second one is this, first one has wavelength lambda, second one has wavelength lambda plus delta lambda. So, what we are interested in is in the slower oscillation, because that is the modulating envelope. So, I am not going to write out the faster oscillation part. So, let me just write out the slower one, just worry about that. So, I have written down the resultant, and as I said, I have kept only the modulating envelope part. There is one more cosine term which I have not written down here. We do not need it for the way we are solving it, and also I do not need the time part. So, let me choose t to be equal to 0, because the result is valid for all the times. So, it does not matter what time I choose. So, if I choose t equal to 0, this part will simply go to 0. So, it is cos of minus some quantity, which will be cos of that quantity, because cos of minus theta is cos theta itself. So, I am going to be left with 2a times cos of half 2 pi by lambda minus 2 pi by lambda plus delta lambda into x. So, I need to crucially use this information that delta lambda by lambda is smaller than 1. So, for that I need to simplify this. So, this will be 1 by lambda minus 1 by, take lambda outside, that will be 1 plus delta lambda by lambda. and now you can take 1 by lambda outside. So, that is going to be 1 minus 1 by 1 plus delta lambda by lambda, and this can be this one can be taken in the numerator with the power minus 1. So, that is going to be 1 by lambda into 1 minus 1 plus delta lambda by lambda whole to the power minus 1. And now, this one we will use the fact that delta lambda by lambda is smaller than 1 and do an expansion, binomial expansion, and keep only the first term. So, if I do that, I am going to get the following, that is going to be 1 by lambda multiplied by 1 minus. So, this will become 1 minus delta lambda by lambda. So, now it is an approximation. The approximation is delta lambda by lambda is lesser than 1. So, 1 and 1 would cancel. So, I am going to have delta lambda by lambda square. Okay, I will now substitute this expression for this quantity that I have just derived. So, it is going to be 2a into cosine of 2 pi by 2 multiplied to delta lambda divided by lambda square, and that would be 2a into cos of 2 and 2 would cancel. So, I am going to have pi into delta lambda divided by lambda square. At what points zeros of this function occurs? So, cosine function would go to 0 whenever the argument, which is pi times delta lambda by lambda square, is equal to some integer plus half times pi. So, this function, which is simply the modulating envelope, this will go to 0 at certain values of the argument of the cosine function, and that happens at these values when pi times delta lambda by lambda square is equal to j plus half into pi, and j is simply integers. Of course, there would be negative integers as well, but it is not of interest. In fact, we are just interested in finding out the value of x, which I seem to have forgotten here. Let me put that in here. So, I just wanted to find out the value of x between two such integers, and if you do that, it is very simple. So, I will get this relation that x is equal to lambda square by delta lambda. So, all it tells me is that the distance between two successive zeros is x, and that is equal to lambda square by delta lambda, but what I want to know is how many full wavelengths are contained in it, and that would be simply equal to x by lambda, where lambda is the wavelength. So, x by lambda will give me a number which will be the number of wavelengths contained in it, and in terms of the equation that I have here, x by lambda will be equal to lambda by delta lambda.